I wanted to make an announcement before we got started. When I gave my talk, the opening talk of the meeting, I mentioned a paper by Freeman Dyson called Gravitational Machines, and several people expressed interest in this paper. So at lunchtime today, after this session, any graduate students or postdocs who want to can join me in the Nambu room left. It's just directly across the hallway here. And we will read through Dyson's paper together. It's only 5 pages long. So if you want to do that, if you're a graduate student or a postdoc and you want to come, just get your lunch on a plate and then come into the Nambu room across the hall. I think we have special permission to bring food into there. We're not supposed to, but I think it's allowed this time. Thanks.
Oh, no, it's just one second. Yeah.
Okay, welcome everyone to the second half of, or second part of the modeling session. The way we have organized this session, the panel discussion session, is we'll have a very short discussion by the panelists who have not spoken yet for 5 minutes, followed by 5 minutes for question and answers. And then eventually we will get all panelists here in front so that you can discuss with them. So our first panelist today is Martha Coglioni, and she's from University of Balearic Islands. And can you change the slide?
Yes.
Martha, so you have 5 minutes to discuss this.
Okay, thank you. So I just wanted to introduce a few questions. The way I was foreseeing this was very interactive, so I just wanted to pose some problems I think are relevant. And the first question actually was already covered by Frank, but I just wanted to elaborate more on that in the sense that, well, the posterior distribution that you see, for instance, in LDK papers, sometimes they combine different results from different waveform models, and this is a way to account for waveform systematics. You know that different models might return different answers. But there are other ways to incorporate waveform uncertainty or waveform disagreement in at inference time. You can, for instance, add the choice of your model as an extra parameter in your inference. This is something that's called hypermodel sometimes in the literature. And effectively, you can guide your sampler towards the model that you trust. The more you can put, for instance, some prior on the choice of the model that depends on the mismatch against numerical relativity simulations or numerical relativity surrogate. Or as Frank said, there is another way that is more fundamental at the level of the waveform models. You can try to incorporate some uncertainties in the form of uncertainty bands on the amplitude or phase. This is very similar to what is done with calibration envelopes, for instance, that are calibration uncertainties are marginalized over routinely in LDK parameter estimation runs. And my question will be for the audience and for other experts, what is the preferred way to go about it? And is this something that we should prioritize more? Because currently a lot of the models that you can find, they don't include uncertainties natively. I mean, there are people working on it, but all of the models that you have in last simulation or open source codes, they don't have these error bands. And also, how do these error bands are useful rather than, you know, applying other methods like at inference time when you want to constrain extra parameters like Frank said, if you have maybe a test of GR, or you want to constrain the properties or environmental effects. So this is question number one. Should I just leave some time for discussion, or I go through all the questions and then, okay. Then the second question was, what should we prioritize when trying to cover extreme corners of parameter space? Both Harald and Frank showed some plots of these famous or infamous event from the last LDK analysis that showed extreme disagreement among different waveforms. And we know that our models have several shortcomings. For instance, waveform for comparable mass binaries, they are very limited when you push the eccentricity to high values. We have a problem for highly spinning, high processing systems. But for highly spinning systems, for instance, there is an intrinsic limitation because also numerical relativity waveforms are not so numerous there, and there might be a really intrinsic problem that it would be nice to hear about having such waveforms, for instance, related to the construction of initial data or other technical issues that Harald would comment on. And likewise, for extreme configurations like in MRIs, you can have extremely eccentric systems. And recently they realized that even current fast adiabatic in spirals that cover eccentricities up to 0.9 are actually insufficient for some of these extreme systems. So should we get more feedback from the astro community to understand exactly what parts of parameter space we need to prioritize in our waveform modeling? And the last question was about environmental effects. So in some models, there's kind of straightforward ways to include some simplified prescriptions to model environmental effects. Sometimes you can just add some extra dissipative channels and then add some phasing corrections. But are these enough? Should these ways of incorporating environmental effects be more thoroughly validated against fully numerical treatments? How can we balance accuracy and computational feasibility? I mean, could we just foresee using simpler templates or simpler descriptions, for instance, for detection, and more complex templates for source characterization? So these are my questions.
Okay, thanks, Martha. So we have about 5 minutes for any questions on these topics.
Can I start from?
Yeah.
So, yeah, I agree with this thing that you have to take the waveform uncertainties into account because based on depending on the waveform, your parameter estimates are different. So if you take the waveform uncertainties, but this is also leading to very broad posteriors, right, for the parameters. But if you want very high precision science to do, for example, if I want to measure the kick velocity, or if I want to measure the tidal deformity, in those kind of inferences, if my posteriors are very broad for masses and other things, then I'm not sure like how we would like address this. Yeah, so what I saw also, it depends exactly on how you model the uncertainty, because the uncertainty you can model in different ways, and depending on also on how you marginalize over the uncertainties, the prior that you put on the noisance parameters that you get from the uncertainty are very important and might kind of change the width of your posterior, sorry. But also on the other hand, I think from my perspective, it would be kind of safer to say, I have a broader posterior, and this is what it is, because I have a limitation that is due to the finite accuracy, for instance, of the numerical relativity simulations that I used to calibrate my model, or from the fact that I have so many of them and they don't cover the full parameter space, so I will have extrapolation error outside of this regime. So it's, in a way, it's safer because it avoids false claims, you know, of accuracy that you don't actually have or you can't guarantee, I think.
Yeah, so I had a small maybe answer or comment on the way forward. So when you say, so basically you have, wave models which degrade in corners of parameter space, or maybe in Harold's plot, it was like the white zones. And one possible way forward is to do hybrid models, essentially, to say that in a region of parameter space, which is kind of in between two methods, well, you can actually use a hybridization of those two methods. So one thing we're doing, for example, in self-force is that at adiabatic order, you can use self-force results, which are very good, and we can do it very well. But then at post-adiabatic order, there's a big program in self-force to do this, but it's very hard. So if you instead plug in post-Newtonian results, which are less accurate, but we have more throughout the parameter space, seems to be good evidence that such models would be very good, for example, for intermediate mass ratio spiders.
Yes.
And I'm thinking with numerical relativity, there's things to do as well with post-Minkowskian for high eccentricity. And this requires also understanding like the dictionaries between these two languages, which is currently the main challenge.
Yeah. No, this is, I completely understand. And this is something that many waveform developers have been working on or are working on. And even in phenomenological models, we are doing that exactly. Because, including gravitational self-force information is very appealing because you can go to higher mass ratios, although it seems that it gives you quite good results also for more comparable masses with what was expected many years ago. And we try to incorporate this information in the ISPAR for the moment, because there is no mergering done for the GSF waveforms. And likewise, also SUB or TUB RISAMES, they've tried to incorporate this information in the construction of their models. So I think this idea that you have to follow a synergetic approach is there. And it's sort of intrinsic also in the piecewise construction of the models that in the end, they leverage several formalisms, post-Newtonian, but also black hole perturbation theory and so on. So yeah, for instance, the gravitational self-force, the other very appealing aspect for me is that at linear order in mass ratio, I mean, the first linear order in mass ratio correction beyond geodesic is essentially exact to all orders in post-Newtonian, in the post-Newtonian expansion. So, yeah, definitely, that's a good strategy to follow.
I had a comment that's in the question. I think it's not just for you, it's also for Frank and for Harold about, and you mentioned it, so you might want to answer, but it might also be a topic for the discussion later. It concerns calibration. So Frank made the point that systematic errors, for example, in modeling the waveforms are going to exceed the statistical ones, meaning that sort of the fluctuations of detector noise are actually going to be smaller than the uncertainties in the modeling. But there's another source here of uncertainty. The instrument itself, you can view it as something which it takes in the gravitational wave that arrives in the universe. It passes that through a linear filter, and then it produces some output. And that linear filter is composed of the optical response of the cavity together convolved with the feedback loop of the instrument. And so when the instrument data is taken, but before it goes to the data analyst, that filter is inverted. That is to say, the output of the instrument is now corrected to account for how the optical cavity and the other parts of the instrument responded to the gravitational wave. And that calibration model is not so precise. I remember Vladimir Baginski, one of the experts in this field many years ago, telling me if you want to calibrate something to 10%, that's straightforward. You want to calibrate it to 1%, you have to work really, really hard. You want to calibrate it to 0.1%. This is an entire career, and you might not be able to get there. So I wonder whether we're actually going to be limited as much by calibration uncertainty as by systematics. It seems to me that's an important point which I haven't heard discussed, and you mentioned it. So I wanted to ask the experts what's known about that. Is the instrument calibration in amplitude and phase also going to be a limiting factor here?
Frank?
People have looked at this a little bit. I mean, in this one plot by Pura and Hasta, they even include the current calibration envelopes that you can see from LIGO data what kind of mismatch they would lead to, and the level is 4 orders of magnitudes below what we have currently for waveforms. And one of the, that's what they quote. I'm not saying, yeah, one of the things that we found when we did this analysis with Sumit is that, as you say, that there's calibration uncertainty to sub% level, let's say in the phase. But this is, you know, at every frequency, there can be a little bit, the phase can be a little bit off. Whereas the waveform models that we talk about, if I have a sub% error in my frequency evolution, this accumulates in the waveform to several radians around merger. So the amount of uncertainty we have in the waveform is actually much larger than, you know, these random miscalibrations that show up at various frequencies.
That actually probably explains it. So so then probably they're not wrong, because the typical phase errors might be a few degrees or something like that. And the point is, it's the accumulated errors here in the waveforms that matter, right? And presumably the amplitude errors are much less important. Yeah, okay. All right, thanks.
Okay, are there any other questions from audience? Okay, so let me ask the speakers if they want to add something, at least on these topics. Finally, Arun, would you like to? Okay, okay, so thanks, Martha. Let's thank Martha for this nice summary, posing these very relevant questions that we should worry about. We'll move to the next panelist. We'll have the slides soon. Sorry. So our next panelist is, yeah, sorry for mixing the order. Yeah, MVS Saket. He's currently at ICTS. I just learned. Okay, so yeah, so again, Saket will walk us through these problems, and then we have some time for our discussions. Thank you.
Hello, thank you for the opportunity. So I work mostly on analytical methods used to build waveforms, whether it is post-Newtonian, post-Minkowskian, or perturbation theory. So therefore, my question is also about the way we apply and use analytical results in order to generate waveforms. So typically, when you have something like, say, a post-Newtonian result or a post-Minkowskian result, you cannot just directly use that in a waveform. Well, sometimes you can, but often it turns out that you need to put it in some kind of resummation, or you need to put it in some kind of model or some kind of calibration. So I guess the question that I broadly want to ask about is, do we have enough systematic and physically motivated guiding principles for such resummations? Now, of course, there are some models, such as the effective one-body formalism, in which you can say that the guiding principle, well, there are many, but one of them is to ensure complete consistency with the non-perturbative, with the non-perturbative test body limit. But that might not necessarily be the best way in all cases. For example, there are also in recent times waveform models that aim to only use the analytical results for the in-spiral or the pre-merger portion, and then use surrogates of NR simulations for the post-merger portions. So in these cases, what other resummations can we come up with? And of course, there is the common technique of using the path resummation and then comparing or calibrating with NR. But are there physical principles that we can also use to do that better? Now, this is, of course, a very broad and generic question. So let me refine it by making a connection to a precise physical situation. When you have a pair of neutron stars or a black hole neutron star system, tidal effects become quite important, because ultimately that is one source by which we can constrain the equation of state. So in this case, if you look at the phase, for example, given by the NR tidal V3 model, it looks something like this. You have the static blue part, the first K effective T, which you can say as something that we completely understand from an analytical point of view. It is a static Love number or the static tidal deformation. Then you have this orange factor, which is partly physical and partly phenomenological. It is partly physical because it comes from the intuition that a tidally deformed object will behave like an oscillator, like a simple harmonic oscillator that is driven by an external force. It is partly phenomenological because we don't really know if that is true for relativistic compact objects. And also we are neglecting all the higher modes and other multipole effects. And then you have this third piece, which combines phenomenology, numerical calibration, and analytical results. For example, you can see this Pade-Risummed kind of fraction. The blue pieces are analytical. They come from post-Newtonian considerations. The red pieces come from numerical calibration, as in we don't know these coefficients and we match with simulations. And of course, the fractional structure itself is again phenomenology, because we do not have any reason to really resum it like that, except that this is something that the people, the authors of Anatidal V3 came up with, and it seems to work well. So in these cases, the question that I want to know is it worth putting in efforts to refine our analytical considerations to maybe capture some of this phenomenology into the analytical results, or perhaps to find a different calibration that will give even lesser mismatch? Or does it really not matter and it is sufficient as long as we have a model that gives a sufficiently low mismatch with the numerical simulations? Now, as someone who works on analytical directions, I would like the answer to be yes, that you should include more physical effects to capture more of the phenomenology into your analysis. The reason being that ultimately, if we have enough simulations to cover the entire parameter space, then why are we even doing analytics for? The idea would be that we have to push it to parameter spaces where we do not have enough simulations, and then we should need to be confident in our results. So to the people who work on neutron stars specifically, and also more generally those who work on phenomenology and waveform detection and parameter estimation, if tomorrow we find a neutron star simulation and we recover some love number from it, we know we are not just using the 100% known blue pieces, 100% analytically known blue pieces, but also these phenomenologically known and physically motivated considerations. So is there a chance that we will be inferring the wrong equational state or sufficiently wrong equational state? And therefore, is it worth to put efforts to capture more of the truth based on analytical consideration? So yeah, that is all I wanted to say. Thank you very much.
Thanks, Saket. We have the floor open for questions. So I think yeah.
I think if we, the current model, this NR tidal waveform model, which uses some kind of fitting form, but calibrated to NR simulations. Hello? Yeah. And so any kind of fitting function which is calibrated to high resolution NR simulation, high fidelity simulations would suffice to capture. But I agree that we may not be able to capture different physical effects, for example, spin, tidal coupling, things like that. And for that, these different terms are required. So,
yeah, very nice presentation. So in the case of binary neutron stars, where the spins are not perpendicular to the orbital plane, the tidal forces would cause precession also. So how do you model these when the precessions are going, and the rate of precession would increase as the two neutron stars approach each other? Whether these effects would be dominant during the coalescence, and how do you take into account the modeling?
There are works on tidal effects in spinning neutron stars, but the specific case of spins not being perpendicular is something that I'm not very familiar with, but perhaps Professor Tanya Hinderer can answer this question.
Saurabh?
Could you please give the mic to Professor Tanya?
Well, yeah, so that's a bit underexplored. There are some works, as Sarkar said, on also, yeah, including tidal talking effects. But I guess this has not been a priority because we think neutron stars will not have strong precession because they're not so highly spinning. So, I mean, it should be done for sure, but yeah, the priority has been other effects first.
hello?
However, familiar with the fact that spin can be quite significant for neutron stars. I think over the last year, there has been some controversy about waveform models not matching with simulations, but they were all for anti-aligned spins, spins anti-aligned with respect to the orbital angular moment.
I was a bit curious, these phenomenological terms, what are the constraining pieces of evidence there? How do you go about doing the phenomenology?
That I'm also raising. So generally people consider some kind of Pade resummation, which is a rational function of two polynomials, like you see here, and then they try to fit it. That's how you get those calibrated parameters as well. And then whichever works best, people use that. Other than that, okay, I guess some considerations can be made. For example, you would expect the tidal effects to grow with X rather than decrease, and that is why the numerator has a stronger power in X than denominator. But those are just things that you see in hindsight. I don't think they are taken as input, but someone else may know better who works on those.
No, I was basically coming from the astrophysics. So let's say that tell you more about what these pieces should be from the observational side. Are there any constraints?
Actually, no, that they are not. In fact, it's because we do not know how to capture the physics encoded by them that we use those terms there. So in some sense, that's the whole question. Should we include more physical effects to capture them? We can never entirely capture them away because ultimately any perturbative scheme will fail close to merger. But perhaps capturing more physics means having a more robust calibration as well. I mean, with lesser fitting.
Okay, so we have a question from Sumanta.
Yeah, hi Saket, very nice presentation here. So my question is, you have the standard tidal love number term at 5 p.m. and then you have the additional corrections, which will also involve the dynamical tides at some order.
Orange
right?
ones are dynamical tides in some sense.
Yeah, maybe the 3/2 term, right? Or x cube term.
No, I mean the orange bracket term. So the capital omega square, there is the orbital frequency.
Yes.
Denominator. So that is essentially a dynamical tidal effect. It's a resonance effect.
Correct. So along with that, you should also have dissipation terms in the problem. So my question is, in the future generations of detectors or even in the present generation with future runs, what is the possibility to detect these dynamical tides? Do we have an estimation of the number that we have, like for standard neutron star that we have seen, GW170817? We know it is of the order of 100. But do we have an estimation for dynamical tides? Can that be comparable to the static tides and so on? And yeah, in general.
So correct me if I'm wrong, those who know. But right now, when we say we are detecting static tides, we are really detecting that orange bracket as well. So in some sense, we do include dynamical tides right now. Even we're not just including the K effective T when we do recovery from waveforms. Which means that in some sense, we are assuming a certain model of dynamical tides and we are recovering that effect. Without that, the effect might be quite weak, even as the frequency grows during in spiral. As for correcting the orange term, which is what you're saying indirectly, that if you want a true dynamical tides, you want an orange term that comes from relativistic considerations and not Newtonian intuition alone. And I think definitely in the future, it will be possible based upon the talk given yesterday about the importance of neutron stars with third generation detectors. As for dissipative effects, it's more complicated because as far as I know, the naive tidal dissipation that you expect from electron-electron scattering, for example, the shear viscosity that it produces is quite low, and the bulk viscosity does not contribute very strongly either. But there have been recent papers on how the presence of hyperons inside the core of neutron stars can lead to strong bulk viscosity, which could lead to more stronger dissipation.
Arun?
Yeah, thank you for the slide. I think you're raising very important questions here. Let me give my opinions about some of them. The question one about, say, party resummation or doing resummations. Resummations can be remarkably powerful. The difficulty is it's generally really difficult to know when they work and then they don't. There's a famous quote in numerical recipes. Party resummation works amazingly well, except when it doesn't. So the only guiding principle I know is a very simple one, that if you somewhere have a singularity and you're sure where it is, factoring it out helps. Besides that, I think it's essential to keep on testing against other ways of solving the same problem. For instance, in the EOB world, where many different resummations have been tried over the years, ultimately it was agreement with numerical relativity that discarded some and kept others. There's even a paper some years ago called The Ineffectiveness of Party Resummations, pointing out that just because party resummations work at order Pn2 and 2.5 and 3, there's absolute no guarantee that they're continuing to going to work at 3.5 or 4. So it's it's very fragile. You need additional means to test what you have. For the phenomenology and whether to put in more analytic consideration, again, what I have in my mind is my memories from past EOB models. At some point, there were non-quasi-circular corrections, NQC, which were based on various physical arguments why you should get a term like p squared over r or whatever as an additional term somewhere in the model. And as the goal was to make the model better and better agree with numerical relativity, more and more of these things were added. The model became remarkably cumbersome with many, many free parameters. And then after a few years, some other change elsewhere in the model made all these extra terms unnecessary and they disappeared again. So before one puts in more effort, I'm not sure what the right order is. So doing more analytical things is always nice, but only if whatever you're putting in is actually present in the true physical system. If you're accounting for a 1% deviation of something that's elsewhere off by 12 but 10%, then the 1% effort A doesn't matter, and B might actually be a fool's errand because you've now begin putting more parameters into a part of your model where it doesn't, where it's not effective. So again, the best answer I have here is one needs to have other ways of getting the same answer, which in this case, I guess, is numerical relativity, and be very much guided by numerical relativity in what type of changes to make. On the other side, sometimes this type of analytic changes, I'm thinking of writing the waveforms as a product of corrective terms instead of a sum, which was happened in EOB a few years ago, turned out to be amazingly well. So there is no clear-cut answer, I fear.
Thank
I just wanted to follow up on that. So I agree that when you have resummations which are kind of guessed, like Pade resummations, it can work and it cannot work. Some resummations can be guided, as I was saying before, by looking at different methods. So you're talking about singularities. If you know from self-force, you have one singularity. You can factor that out in PN, for example. That tends to work well. Or another example, you have these enhancement functions for eccentricity in PN. You don't know an exact form for this. You can do a small eccentricity expansion, and this has led to claims that PN breaks down for high eccentricities. But you can actually compute the behavior of these enhancement functions when E goes to 1, so large eccentricity. So you have an analytical expression for E goes to 0, E goes to 1. You create an expression which captures both. And since these two things are physically meaningful, it's actually extremely accurate throughout the whole eccentricity parameter space. So I think the guiding principle for resummations should be like information from different methods, which is secure.
Yeah, that makes sense.
Okay, so I realize we have some questions, but they are from panelists. They will anyway come. So Kenta and Martha, I'll come back to you for your remark. We can move to the next panelist. Our next panelist is Professor Alok Laddha. He's at Chennai Mathematical Institute, and he will speak to you. Can you say something? Can you say something?
Yeah, can you hear me?
Yeah. Okay.
Okay,
So,
so
yeah.
I should, well, let me first, before switching the slide, say that I should actually thank the organizers and also not thank them because they are giving me, they have told me to summarize amplitudes in 3 minutes before raising my questions, which is kind of a hopeless task. So for people who have never, so as I think most of you have heard, there is some relationship between quantum field theory amplitudes and gravitational waveforms. So let me just tell you in one line what an amplitude is in case some of you may not have heard of it. So if you take two particles which start from the far past, very, very far away, and what amplitude does for you is computes a probability that in the far future you will get, let's say, two particles with some velocities and say 10 to the 23 gravitons at some angle in some detector. So that's what amplitudes do. They give us probabilities for outcomes once we start with some initial state. So given that definition, let me just first briefly review what the basic idea of this program is, where you go from amplitudes to classical, gravitational waveforms. There is one catch which is often forgotten in all these discussions, is that these gravitational amplitudes, is also called an S matrix, actually it's ill-defined in 4 dimensions. And this is because of a reason which is called infrared catastrophe, which is actually quite easy to understand. So the idea is that if you take any scattering, let's say 2 particles which scatter, and they scatter into say 2 particles and some gravitons, you can always ask what's the probability of emitting an arbitrary number of gravitons which carry almost no energy, very low energy, and that probability will always be non-zero because gravitons' energies can be as small as you want. But because the total probability is 1, if you start with some fixed incoming configuration of particles, probability for it to scatter to a fixed outgoing configuration will obviously be 0, because somewhere all possible outgoing configurations should add up to 1. Then we should ask, okay, if S matrix itself doesn't exist, then how can we ever do anything with it to get gravitational waveforms? And the idea is that even though S matrix doesn't exist, there are some observables you could construct from them, which are usually called inclusive observables, which do make sense and they are finite. And the way they are defined is basically by asking some sort of conditional question. So one of the questions is, you start with some in state, let's say 2 black hole state, and you ask the questions about how much energy is emitted or flux is emitted, to a detector at null infinity, regardless of the outcome of the black hole. So you sum over all the configurations of the black hole. So that's like a conditional question, and that turns out to have a finite answer. And actually, this is the reason why even if the S matrix itself doesn't, it's ill-defined, classical observables can be generated from this amplitudes. And the way this thing is, so these ideas have been in the literature of quantum field theory for a long time to get classical observables from amplitudes, but they were sort of systematized by 3 physicists, Kosover, maybe and O'Connell, around 7-8 years back. And their idea is very, very beautiful. And the reason there are many ways to connect amplitudes to gravitational waveforms, but the reason I'm summarizing this idea is that this is like a purist idea where you really just start with S matrix and go to, you go to classical observables without using matching or anything like that from effective field theory. So the idea is that you start with some fixed 2-body incoming state, let's say with some separation of your black holes, and you compute, for example, you can compute, say, scattering angle like we do in classical scattering, or outgoing radiative flux, etc., irrespective of what the outgoing matter configurations. You sum over all the possible matter configurations, which is why this is it's like this class of observables. And this formalism is like formalism. It's a very beautiful formalism. It's very clean, but it works very, very well if post-Minkowskian expansion holds, because it's in that expansion that you can do perturbation theory and compute these amplitudes. And the answers are obviously then for hyperbolic scattering in the classical theory. And one interesting aspect, which is probably good and bad, is that it treats all the conservative and dissipative effects democratically. So if you're at some order in post-Minkowskian expansion, in KMOC formalism, you can't really isolate like a conservative sector and a dissipative sector, simply because amplitudes, because of unitarity, they dictate everything. Whatever scatters, and we can't control it. And in principle, any order in post-Minkowskian expansion, including radiation reaction effects, they are just included thanks to the unitarity of S matrix. So in that sense, it's really a amplitude first approach. Now let me, with this summary, kind of useless summary of amplitudes and waveforms, let me give you some other questions which has puzzled me over the last few years. So one is, for example, how does one derive concrete result for bound orbits, which is of most interest for audience in this room. And of course, there are some ideas, especially if you look at conservative sector, where you assume that there is no dissipation by Porto and their collaborators, which are very beautiful results, which tell you how to map results for hyperbolic trajectories to bound orbits. But and even though there are some ideas about what happens if you have if you take dissipative effects into account, where eccentricity will decay, like it's not entirely, in my opinion, clear how such a map works. Another question is, in classical GR, we of course know Kerr black holes are non-linearly stable. This was derived by Christodoulou some years back. But beyond one first post-Minkowskian expansion, there is no first principle definition of Kerr black hole scattering, especially when you take gravitational radiation into account in quantum field theory. So there are, of course, beautiful EFT approaches. We rely on post-Minkowskian as well as spin expansion. But at coalescence time, such expansion, it will break down because black holes will spin very, very fast. So it's not entirely clear how do you quantify this in terms of like purely amplitudes of two Kerr black holes. Non-perturbative scattering is not amenable in this formalism because we don't know how to compute non-perturbative amplitudes in, even in Einstein's theory. So these formalisms really always rely on, if you want concrete result, on large impact parameter scattering, where the exchange momenta is very, very small. But we know that, in classical GR, there are effects like memory and, your tail effects. And in fact, these results are not even strictly speaking from amplitude perspective, that they are valid to all orders in post-Minkowskian expansion. So for example, if you are given some head-on collision of two black holes, then there are like a hierarchy of soft terms like memory and its tails in hyperbolic scattering, which are exact to all order in post-Minkowskian expansion. So it's not very clear how to derive these classical results, which are non-perturbative from these approaches like KMOC, which rely on having amplitudes which are perturbative. So yeah, well, this is related. I mean, can we compute amplitudes? Can we use amplitudes to compute memory and all its universal tails? And there are these. One of the surprising results that came out of looking at hyperbolic scattering was that some really interesting universal tails were discovered by Ashok and Vishwajit and others. But it's not very clear how to relate these results for hyperbolic scattering to bound orbits, where we also know such memories and tails exist. But as far as I understand, no clear map has been quantified. I mean, we don't really know exact map between these things. So maybe I stop.
Thanks, Alok. We have some time for a few questions. Patrick.
Am I audible? Yeah. So if we take the usual photon radiation from a bound atomic state, then the way one goes about is that the initial state is the atomic quantum state and no photon, and the final state is the quantum state jumps to a lower level and a single photon, and you sandwich it between the operator, the dipole moment operator. So in this case, the bound state can be, if you assume to begin with the two mass points to be very, very small. So and you treat it like a hydrogen atom problem, but with Coulombic, the gravitational gm square by r potential, and ask the same question, that initial state is one of the bound quantum state of the two body bound state, and zero graviton state. And what is the final state? It goes to one level down or lower level, and one graviton. The operator, relevant operator, is the quadrupole moment operator.
Yes.
Has this been tried?
Yeah, this has been tried, yes.
Okay.
But I think we are asking a more general question, because in relativistic quantum field theory, even if you start with a bound state, you have to track the evolution, right, of whatever state you have. And so as it emits more and more gravitons, it will decay, and in the end you may get like a single state, right? So if you look at the full amplitude perspective, where you don't do a non-relativistic or semi-non-relativistic computation, then that's what you are doing, because you want highly accurate waveforms. You want to go higher and higher order in post-Minkowskian expansion. So, but what you are saying would agree. I mean, that has been done.
Okay. Are there any other questions from?
Yeah, I think maybe we can ask the other panelists to come and sit by the time we. Right?
Yeah. So can I request the speakers of the morning session as well as the panelists?
Just a clarification. What do you mean by non-perturbative scattering is not amenable in the KMOC?
Because if you want to do a computation of scattering in Einstein's theory, it's very, very hard, no? Because you'll have to do string theory, for example. If you take two particles and just let them collide.
You don't expect to get the memory and tail effects from a perturbative.
Well, yeah, that's what I'm saying. So maybe we can talk about this later. We know that memories and tails would exist even for collision, but we don't know how to derive it from this formalism.
Okay, thank you.
Yeah, look, I had a quick question about your bound orbit mapping. So in the post-Newtonian theory, we know that certain analytical continuation can take you from hyperbolic scattering to that. So wouldn't those things be applicable?
No, I mean, this is because it's post-Minkowskian. So I think but I mean, if you assume that eccentricities don't decay, then map is well defined. But I'm saying that in general, if you just really look at, like in KMOC formalism, where you have no control, where eccentricities are decaying, then to me, it's not entirely clear what these maps are.
Okay, so if there are no further questions, we move to the
You should sit
the last part of the
seat for you in the middle.
take the center stage. Bruce?
So I'll start off with my first question for the panel, which is, why is it important? I can understand the importance of getting very precise waveform models for testing GR. But let's just say that if we assume GR is correct, just assume that for a moment, then do I need to know the spin to 3 decimal places? Why, what's the motivation for highly accurate waveform models other than testing GR?
I guess I have the microphone, so I'll answer first, and Frank also has at least something to say. It's not about 3 significant digits for the spin right now, but of getting the first digit of the spin correct. So we are by far not at the 3 digit level. I think the 2 primary answers I have is the detectors we are building or wanting to build cost billions of dollars, billions of euros, billions of your favorite unit. And so we should do as good a job as we can in exploiting them to the best of our abilities. In the past, also, with higher precision, more uses for observations came about. For instance, the pulsar timing results who get the masses of the pulsars to 3 or 4 significant digits, one could similarly ask why. I think it's really cool being able to do this, so I'm not questioning pulsar timing in any way, shape, or form.
Yeah, I mean, one thing is that I think the accuracy of the measurement and the accuracy of the waveform, or the precision of the measurement, is not, they're not necessarily correlated. I could use a Newtonian waveform and estimate the chirp mass of a binary neutron star in spiral, and if the SNR is high, I would get a very precise estimate, but it would be inaccurate. So, you know what I mean? So the number of digits that the measurement seems to give me depends on how good the data is, and we need to get the models accurate enough so that they live up to this precision that the measurement is capable of. Although I do agree with part of your question, yeah, but I do agree that I think for several astrophysical implications, it would be fine if we could construct a model that is fast and accurate but less precise. I think many of the astrophysical studies that we do would still work fine. Last comment on this: once we start subtracting signals because they overlap, then this subtraction better be as good as we can, I think. Otherwise, we'll bias the other measurements.
Okay, I think I'll leave it at that. I'm not gonna.
I think it's also like when you add more physical effects like eccentricity, for instance, we had this NSSB achievement where if you would have used eccentricity effects, we wouldn't have never found that there was an eccentricity effect or spin precision, for instance. I mean, I think adding more physical effects and more accurate waveform models really giving you more information about the source as well, and hence the astrophysical population inference as well. So it's, yeah, that's all.
Okay, Shashwat.
Okay, now I'm audible. Yeah, a related question. We started with just masses, then we went to aligned spin, then we went to precessing spin, and now we have eccentricity. In your opinion, what do you think is the next most important parameter to include? Or is it that you take an existing parameter like eccentricity and push it to say greater than 1? So now you have unbound orbit. So what do you think is the next thing to do?
Martha, yeah.
Yeah, I had the microphone, I had to talk. No, I mean, it depends on what you want to constrain, I think, because even eccentricity, the models can be heavily improved still, because the latest aligned spin models, including eccentricity in higher modes, they show the grading performance as you increase eccentricity. So that's already something that we know is not perfectly modeled, and the same is for precession. As soon as you have strong precession, there have been many injection campaigns where you inject numerical relativity waveforms with high chi-p, and you recover with different models, and you see a lot of biases, especially when you go to more unequal masses. So all of these effects that are not particularly fancy, they are not beyond GR or anything like that, they can still be improved a lot to inform also astrophysical models.
Yeah, and maybe, so the way you formulated the question seems like, you just want to add new effects more and more. I'd rather say that I think that detectors that we have now, like we expected more vanilla systems, right? You have circularization. We don't expect to have huge eccentricities or huge. So a lot of the effort was to try to do the easy thing very accurately, which is circular orbits on spinning. Future detectors, I mean, we're expecting basically every possible kind of system. So basically regarding the accuracy question, I think there's a lot of having these waveform models extremely accurately is good to break degeneracies. For example, we know there are degeneracies between eccentricity and spin precession. And so I would say that the most important thing is to have a model for, 2-point bodies, like, okay, structures are important, but then this is a tidal effects and all these things, you can, it depends on so many new parameters, but the two-body problem, if you just ignore, like, of two black holes, for example, is not that hard. I mean, you don't have that many parameters. It's hard to model, but like, it's a clean system. So I think if we could model that clean system throughout the parameter space, that would be already the main goal, I'd say, to focus on.
Maybe I can ask a question to her also on his talk. So if you go beyond 5 PN and you include eccentricity and spin and everything, do we expect qualitatively new features to come in the waveform? Suppose I do a 6 PN computation versus 7 PN computation, like generic eccentricity and spin. It'll just be more and more precise waveform, or do we expect surprises physically?
Arun?
So I'm not a PN or PM expert, so I don't know what actually is going to happen. On the conceptual level, I believe there is a big possibility for surprises, that new type of effects, new type of terms are going to show up, besides just having the calculation being more complicated. On the astrophysical aspect, I don't know, and I don't think so, that these new terms, these new effects, will have a dramatic impact on the waveform. It's not that suddenly what used to be a quasi-circular orbit because of a 6 PM term is going halfway through the inspiral into a highly eccentric state or anything like that. So I think in terms of astrophysics, the impacts will be quite gradual and benign, but this is just my own expectation.
I agree.
Hello.
Ricardo, you want to add something?
The time-dependent tides, that we start entering at higher order. So having seen the effect of tides, then will allow you to see if there is any departure from GR. If you see an ultra-compact object that is compatible with black hole, but okay, you start seeing things at 5 PN, and then you might have, I don't know, environmental effects if your sources are not in vacuum, there might be environmental effects. So drag forces, the stars at, if I will remember, 5.5. So to have an analytic baseline to which comparing astrophysical effect would be useful. But anyway, at this high PN order, I mean, you only see them close to the merger, and then close to the merger, the description.
Also, there's this notion that tidal effects are 5 PN, which is true formity if you consider that your neutron star has a short radius, which it doesn't. And so, you have big coefficients. So you already can put constraints even indoor order. So it's not like, as if you need to go to 5 PN to say anything about the tides. That's not true. It's just a way of counting things.
Okay, Suresh.
Following up on Bruce's question regarding what is the precision to which we need to calculate. Since our detectors are calibration accuracy limited at the level of 1 to 2% right now, would it make sense to say that the waveforms have to be accurate to that level, and going beyond that is not going to give you much returns? Is that a reasonable approach? No.
I mean, I understand the thought, and in principle, if our errors would show up as, as you say, 1% random deviation, that would, in principle, this argument would hold, but it's not how it works. For instance, if one models the in-spiral rate, if there's a sub-percentage small error, it would accumulate across the in-spiral, and then at merger, one can have several radians of uncertainty.
Yeah, the limit I was thinking about was not so much on the parameters errors, but on the resulting waveforms errors. Because the comparison is between the template and the inherent waveform in the signal, right?
From the overall amplitude calibration, you're not going to get the distance to more precise than 1% if the overall amplitude calibration is off by 1%. So that's a place where, there's no point if you have some uncertainty in the amplitude, there's no point in getting it to 0.01% because the calibration will never be that good. But the part where it does matter is the phase. As Frank said, the phase accuracy, which you have when you do calibration, maybe a few degrees, especially near unity gain points and things like that. That's actually a few degrees of precision is actually very precise. What they're worried about is accumulated phase errors that build up over time, over thousands of cycles, and that can be hundreds of degrees.
So if we put a limit on the waveform of one or a few degrees in phase, that would translate to perhaps 1,000th of a radian or 1,000,000th of a radian in terms of the parameters that they have to plug in order to, that is the error in the frequency, for example, would be much smaller because it accumulates, the phase accumulates. So I understand the parameter has to be much more accurate, but the resulting waveform will still be only accurate to 1%, needs to be accurate to 1%.
I guess I've been sitting here for too long now. I'm not thinking clearly anymore. We should talk afterwards.
Okay, so I think Sumanta, you had a question. You have a mic?
The first thing is regarding Shashwat's comment. I think after eccentricity and spin precision, we may have to think about environments, right? Because that can be the next important thing. So I would like to hear your comments on that.
Martha, okay.
Yeah, this is why I put out that question, because a lot of us are doing waveform modeling from a very privileged position, that is vacuum, binaries evolving in vacuum. And yeah, I completely agree that that's something that we need to worry about. And the other aspect that I wanted to raise, but I'm not working on environmental effects, so I cannot say much about this, But for instance, what I saw recently in studies of IMRIs and MRIs in spiraling in accretion disk is that they were even considering the effect of stochastic torques, gas torques. So this complicates the modeling quite a lot, because if you can just introduce an extra flux term or modify your forcing function, that's relatively easy now if it's on a closed form expression. But if you have to solve ODEs accounting for these stochastic effects, and it's much more complicated. So, I mean, I guess that, yeah, I would like to know better for which uses do we really need to nail down these very, very tiny effects, or even maybe bigger, but more complicated. And maybe there are some use cases where we can get away with simpler descriptions. But yeah, this is more a question for the audience, because I don't work on this. I don't know if anybody.
Yes, so one of the slides I skipped this morning was precisely about astrophysical effects. I also don't work on them, but I'm very excited about them because at some point they will become visible in our data. And on the one side, they are nuisances if you are the purist who just wants to analyze binary black holes. But on the other side, they can give us immense amount of extra information about the universe, about the accretion disk, about the intervening matter that gravitationally lenses the gravitational waves and so forth. And so as Marta, I don't know when they become important and how to deal with them, but it's certainly something we need to begin thinking about. And coming back to Bruce's question earlier, one way of another reason I just realized of analyzing the binary black holes to as much as we can is to begin to discern any small effects from the environment on top of them, so we can learn about other things. I'm thinking here about the CMB analogy, where cosmic microwave background, you started out trying to do cosmology, but then suddenly you realize, oh, the Seltovich effect now tells you the position of every single galaxy cluster in your in your field of view. Or you learn about the extinction by dust in our own galaxy through the CMB photons. I hope something similar is going to happen with gravitational waves in the perhaps ET, perhaps post-ET phase, but I hope at some point.
Sumanta, you wanted to, yeah.
So I have a question for David, Ricardo, and also possibly Alok. So I think the tidal effect should enter at 4 p.m. for non-rotating case because of tidal heating. And I mean earlier than 5 p.m. And the second comment is when you do EFT calculation, typically there is a near zone, far zone separation. And that is sort of ambiguous. Like it's not very clear like whether it should be in the near zone, what should be in the far zone. And I'm not sure if amplitude can actually help that, because what Alok said, there is no near zone, far zone decomposition, what is required. So can we use amplitudes to compute tidal effects? I do not know, because I have not seen any literature on that. So yeah, any comments would be useful.
Okay, so we do have some papers on computing tidal response coefficients from amplitudes. Typically, we just scatter gravitational waves off of the black holes, and then from the phase, you can extract the tidal response coefficients. The challenge is, as you said, the mixing of various diagrams in EFT. So we need some way to split out the diagrams that are actually due to tidal couplings, and those are due to instead nonlinear interactions between the gravitons. On the EFT side, it is very straightforward. You just drop the diagrams you don't want. The challenge is when you compare with black hole perturbation theory. And that is where, as you said, we need some kind of near far zone separation. Now, we also had a prescription, which was originally proposed by Zihan Zhu and Mikhail Ivanov, in which they do find that the black hole perturbation theory scattering amplitude does naturally split into two pieces, a near zone piece and a far zone piece. And they claim that the far zone piece is purely due to the nonlinear graviton-graviton scattering, whereas the near zone piece is actually the graviton coming, exciting a quadrupole, and then quadrupole re-radiating. And that claim seems to hold at first few orders. We could use that, for example, to show that the dynamical love number of a Kerr black hole is non-zero and exhibits renormalization group flow. But the separation is not still robust enough that we trust it beyond, say, next to leading order. So yeah, it's not clear to me. Maybe someone has a better answer on how to properly filter out the tidal effects or any object-specific effects from the nonlinear interactions. But I think that's less of an amplitude problem and more of a perturbation theory problem. Like, how do you do the matching? Because on the amplitude side, it is relatively straightforward, I think. Yeah.
So maybe I just wanted to answer for the second question about the split. So within PN theory, the split, there is no ambiguity. There is some arbitrary parameter which is supposed to cancel out in final results, which, essentially the idea is that in, for example, flux balance laws, if you want to express your flux at infinity in terms of a quantity at, at your system, well, you need a choice of slicing. So this thing is ambiguous, but if you express, flux balance law with your binding energy at infinity and your flux at infinity, that's not ambiguous, or something in the near zone, as long as, you give gauge invariant results which are do not depend on this slicing, is not ambiguous. Now, it's true that, well, for self-force, when you do comparisons with self-force, for example, they implicitly choose a certain slicing, so a certain value for this B0. But I would say that, there shouldn't be no ambiguity in this near zone, far zone thing. Just, yeah.
Yeah, I mean, just a small comment. So in general, as Saket is saying, that one could compute amplitudes for, graviton scattering of some background. But I think that's the approach where you just look at in and out scattering processes. In general, there could be infrared divergences. I don't know in this context if you go to higher loop orders, if any issue happens. But at least the inclusive observables approach, like where you just look at quantities you can well define in quantum field theory and then try to extract out classical observables. I agree with Sumanta. From that perspective, we don't have there is the computation of tidal effects, as far as I know, from the what we would have called in formalism. Maybe you know him.
So yes, there are infrared divergences, but those divergences are well known, at least at first few orders of corrections. And also there is recently a paper on how to resum these tail effects to a arbitrarily high order. So we can get rid of those divergences, and then we can get the Sommerfeld factor, which takes into account the correction due to these infrared effects, even in the in-out picture. Now, it is true that technically in the in-out picture, you cannot capture dissipation, but there we can use the trick of just computing the in-out scattering amplitude and then replacing the QQ propagator with a retarded propagator. So those tricks do work. It's not robust or completely rigorous, but I think it seems to work. Yeah. It would be more rigorous in the sense that you can keep dissipative effects right from the beginning. But there are also papers that say that at least as far as classical diagrams are concerned, it is sufficient to use Feynman propagators and then just replace the Feynman propagators with retarded propagators at the end of the day. Yeah, but
I don't know if it has been said. Sure, tidal heating is 4 PN for spinless black hole. It's 2.5 for spinning black hole. So yes, but that's absorption. So absorption appears at 4 PN already. And then what I refer tidal effect that appear at 5 are deformations, like oscillation. The fact is appears 5 PN, but in GR they are 0. The tidal deformation of black hole in GR is 0. So it would be very important to measure a non-zero tidal deformation because it would signal a dramatic deviation from GR. And about the near-far zone, so near-far zone is a naming that has been given maybe 40 years ago within the context of general relativity, but over 20 years ago, people realized that the same thing was applied in particle physics, and it's called potential region and radiation region, but it's the same thing. So this concept existed independently, and they were realized later that they were the same thing. But they correspond to something that phenomenologically anybody can appreciate, not even physicists. I mean, there is a gravity responsible for attraction, for internal attraction, and for radiation. Phenomenologically, there are two very different effects. And the beauty of GR is that they belong to the same underlying theory, but they are treated also in a very different way. So one depends, they belong to some region of momenta of the Green function, the region of momenta where the momentum is much larger than the frequency, whereas radiation belongs to the regional momenta where space momenta is the same order of frequency. So mathematically, they are very well defined, potential region and radiation region.
Alok,
So
you have
maybe
quick,
a question for
quick
Ricardo.
remark.
Yeah,
Quick
yeah.
remark, yeah.
Yeah, no, just a question. Like, so particle physics, of course, because we do in Minkowski space-time, we can define near and far in potential region and radiation region. But is there a subtlety with diffeomorphism invariance if we go to, in this split, if we go to high enough order, or? Right, but still we have the gauge ambiguities, right? So, I mean, diffeomorphisms, right? I mean, linearized diffeomorphisms, and at every order, I mean, is there any problem, or is it exactly the same as in particle physics? Okay.
Okay, sorry, I have to, Arunavas, probably you can ask your question during lunch. We have a shorter lunch today, so I have to, end the session now. We meet at 2 for the sparkler session. So let's thank the panelists and the morning speaker once again.